So in previous videos, we've talked about how to use chemical formulas to do calculations from the entire compound to just part of the compound using those subscripts in the chemical formula. In this video and in the next video, we're going to talk about how can we actually calculate something called the empirical formula for a molecule. Empirical formula can be different than the actual molecular formula for that substance. We'll talk about molecular formulas in the next video. In this video, we're going to talk about how we can determine the empirical formula for an unknown compound from experimental data. You will actually do a lab like this. I believe it's your second lab. You will actually determine the empirical formula for a compound that contains magnesium and oxygen. You'll actually do that in lab. What we're going to do here is talk about the math and do the math associated with those calculations. So when calculating empirical formulas for a substance, there are three main steps that you need to do. And I've listed them here, and we're going to do them in a practice problem on the next slide. The first is when you are given information with regards to the mass of elements in a compound, you should always assume that you have a 100-gram total sample. Why should you do that? That makes life easy because that means that if you have a 100-gram sample and you know what the mass percent is of that element, then the grams of that element is just equal to the mass percent. Just take off the percent sign and slap on a gram sign. So for example, if I had a 100-gram sample and 20% of it was due to iron, that means that 20 grams of that substance is due to the iron. So, first step, always assume in empirical formula problems when given mass percents that you have a total sample that weighs 100 grams. That makes the math easy so that you can just take off the percent sign, slap on a gram sign. Second is to use your molar mass and dimensional analysis skills to convert the grams of that element into moles. Then you divide the moles of each substance by the smallest number of moles present in the problem. What that does is that gets your numbers, the results from step 3, into whole numbers. And those whole numbers are the subscripts in your empirical formula. So let's take all those words and do a sample problem. So let's say I have a compound, unknown compound. I know it contains three things. 22% of it is iron, 50.2% is oxygen, and 27.8% by mass is chlorine. And I want to know what the empirical formula for the compound is. The empirical formula is the simplest whole number ratio of atoms in that molecule. Step 1, which I've already done for you, is to take these mass percents, assume a 100-gram sample, take the mass percents, lop off the percent sign, and put on a gram sign. So my 22% mass percent of iron becomes 22 grams of iron. So on and so forth. Step 1 complete. Step 2, convert your grams of substance, your grams of element, into moles of element by using that substance's molar mass, which in this case is for iron, and for oxygen, and for chlorine. Oh, I haven't done the division yet. Let me get my pointer here. I wrote the molar mass of those so that my gram units cancel. Then I go ahead and I do the appropriate division. So 22 divided by 55.85 gets this number. Do the same thing for the oxygen and, excuse me, for the chlorine. So step 2 is complete. I have converted my mass of each component element into moles of that component element. Third and final step is to look at the mole values that you calculated, determine which number is smallest, and then use that number to divide each of these numbers by to get whole numbers. So looking at those three numbers, 0.3939 is obviously smaller than 3.1375 or 0.7842. So I am going to divide all of my substances, all of my mole values by 0.3939. Doing that for each element, I get a great big fat 1 for the iron. For oxygen, I get 7.97, which is close enough to round to 8. We'll talk about rounding shortly in the next video. That number is close enough to roll to round to a whole number of 8. And last but not least, doing this final division for chlorine gives you 2. So now I have whole numbers associated with my elements. Those whole numbers serve as the subscripts in the empirical formula. So my empirical formula is Fe, we don't put 1 if we just have 1, but just Fe, O8, and Cl2. That would be my empirical formula for this molecule. So those are the 3 steps that are used in calculating empirical formulas. One other important point to make, and I kind of hinted to that with the rounding. So in this example, I didn't get exactly a whole number when I did the division, but it was close enough to round. There will be some times when you do your division that you get numbers that are not close enough to round. If you have an instance like that, then you need to multiply your subscript by an appropriate fraction so that you get a whole number. So what values can you not round to a whole number? So the ones that are most commonly seen, I think, in problems that we do in this course are probably this first category and this third category. Although you could sometimes also see second and third. So if you, after doing the division for the moles, if you get something 0.5, like 1.5 or 2.5, that is not close enough to round, you need to go ahead and multiply that value, in this case by 2, so the fraction will cancel. So let's say, for example, I have an empirical formula after doing my division of P1O2.5. I need to multiply both of my subscripts by 2 to get them to be whole numbers. So the proper empirical formula would be P2O5. So when can you not round subscript values to a whole number when doing these calculations? These are the 4 examples, and I would say that the first and the third are the ones that are seen most commonly. The only other extra step you need to do is to multiply by the appropriate number so that your decimal becomes a whole number. And we will do an example like one of these in lecture.